Like you said, you'll conduct request for me.
Okay, I will let you know. I will let you know. For
Okay,
people who
sir.
have missed this, I'll let you know.
Yes, sir. Yes, sir. Thank you.
So I think we'll start today's session. Okay, we'll have a discussion on. We'll complete AES algorithm today, right? So last class we have been discussing. I mean, if you remember properly, we discussed DES. Then we came across AES and we came across the sub-byte shifter rows, and we had a detailed discussion before wrapping up our pre-cat class. We saw how mixed columns happen, right? So I hope you remember how the sub-byte, the state look. Okay, the sub-byte transformation, then the shifting, then mixing of columns, right? So once this mixing is done, then I'm going to perform an operation called addition of key. So addition here, what I mean is it's like a XOR operation. So we'll be having a, since now we are discussing AES 128, okay. Also we are discussing AES 128. This round key will also be 128 bit, will be a round key size. So 128 bit, if you convert them into bytes, it will come to 16 bytes, right? Again, same way, your state will also be 128 bit, that is made up of 16 bytes, right? So we are getting a 4x4 box kind of thing. So I'll be taking each and every column and I'll be performing a matrix addition. So whenever we say addition, it's like XOR operation. Or how we perform the matrix addition, the same way, okay, you'll be getting the final output of the state after adding the key. Right. Now we move on to the next important part, that is key expansion part. So in DES algorithm, we used to call them as a key generator, where you are going to generate round keys for each and every round. So here they are naming it as key expander, key expansion process. Right. That is each and every cipher key which are going to, I mean, sorry, if you have the cipher key which are going to be given as input for the key expander, it is going to produce different 128 bit round keys. Okay. So we'll be having our discussion based on AES 128. So we'll be starting with our understanding with 128 bit cipher key. Okay. Once you are clear with this 128 bit cipher key, how this 128 cipher key is used to create 128 bit different round keys. Okay. So if it is a AES 128, totally I'll be having 10 rounds. Okay. And I have to produce 10 plus 1, that is 11 keys, because if you see our AES algorithm, we'll be having a pre-round transformation, then only our round starts, right? So totally we'll be producing 11 keys. So how these 10 round keys are going to be produced from this 128-bit cipher key, if we people get able to understand those part, then you can able to easily grasp how this 192 and 256 is going to be operating. So we'll be having a detailed discussion on key expansion with respect to AES 128, and we'll compare how this 128 and 192 and compare and understand how 192 and 256 works on. Right. Then we have analysis of key expansion, because if we already saw in DES algorithm, one of the major drawbacks on weak keys and semi-weak keys. Right. How these things are going to be overcome in AES algorithm. Right. So to start off with, once I have been provided with the 128-bit cipher key. So as already said, 128 bit, if I write them into bytes, I'll be having 16 bytes. Right. So how many words are present within the 16 bytes? Can anyone tell? I hope you remember the data units which we discussed. You can use your chat box to say the answer. So 8 bits make 1 byte. Yeah. Yes, Kashish, you are correct. So 4 words. Right. So once I am provided with 128 bit cipher key, the words will be named as W0 to W3. These are the given key. This is your given cipher key. So I'm directly using that cipher key itself for pre-round transformation. Okay, but for rest of the rounds, for example, here if you're going with the 128 bit cipher key, so totally 10 rounds. So this rest of the 10 round keys, I have to expand this key, that is from W0, W1, W2, and W3. the 4 words which I'm going to obtain from cipher key has to be expanded for other rounds also. So how this key expansion occurs? Okay, so this is how the exact part, how the process happens. Assume this is the cipher key provided to us, which is a 128-bit cipher key, and it is been grouped under 4 words W0, W1, and W2 and W3. So this will be directly used for pre-round, right? For pre-round. Okay, for round 1, I have to generate the values for W4, W5, W6, and W7. Right. So here we can able to group the entire key expansion under two categories. One is the words which are in multiples of 4, W4, W8, then if you go with W12 and so on, W16, W20 up to W40. Okay. Generation of these multiples of 4 words will have a separate process, and rest of the words will have a separate process. So how this rest of the words is going to operate, we'll see first. Right. For example, if I want to generate the word W5, I am taking W4. You can able to see I am taking W4 and W1, and I am sorry. Simply you can able to see I am taking W1 to be XOR with W4. Right. And if you see the next one, that is W6. Okay, W6 is generated as W2 XOR with W5. Able to see it's taking W2 and W6. So if you want to generalize this expression, okay, that is if you want to generate an ith word which is not a multiple of 4. Here we are discussing the value of I which is not a multiple of 4. It's nothing but W I minus 4 XOR with W I minus 1. So that's why you can able to see if you take W7, that is if you substitute I is equal to 7. Okay. So I is equal to 7 means W7 is nothing but Wi minus 4. This 7 minus 4 is what? 3. Sorry, 7 minus 4 is 3 plus, XOR Wi minus 1, or you can write I minus 1 or minus 4, whatever way, because you are obviously going to perform XOR operation. So I minus 4 is 3, I minus 1 is 6. So I can able to see W6 XOR with W3, I'm going to get W7. This is the process which is used for generating the words which are not multiples of 4. Suppose if you are going to generate the words which are in multiples of 4 like W4, W8, for this we need to create a temporary word called this T. The word T stands for temporary. So T4 is nothing but a temporary word used to create the word W4. T8 is nothing but a temporary word T8 which is used to create my word called W8. So before generating this required W4, W8 and other multiples of 4, I have to generate the respective temporary words. So how these temporary words are going to be computed? Okay. For example, here this is a general expression, the process, how it works on. Okay, okay, I'll just rub this part, otherwise we'll explain here. Assume that now I want to generate T4. That is, in this case, assume the I is equal to 4. Okay, this I is equal to 4. So for this process, I have to take Wi minus 1. That is, I will be taking W3. Okay, then I have to process this W3. The first process is called this one, rot word. Okay, that's nothing but rotation of words. How in the sense, I'll be making a 1 byte left shift of that particular W3 word. So in this example, your W3 word, this is one, that is K12, K13, K14 and K15. So if I perform operation of a rot word, okay, this K12, K13, K14 and 15, how it will look like in a sense, I'll be getting K13, K14, K15, then K12. That is, this last word will be taken and pushed to the end. Okay, this is a process of rotation of word. After this rotation of word, I am going to perform an operation called subword. I hope you remember we already saw an operation called subbyte inside a round. And the same process is going to be done here. Okay, here in subword, why they naming it as a word in the sense, I'm going to substitute each and every byte in this entire word. Plus the entire word is going to be substituted. So I'll be taking each and every hexadecimal value. So K13 will be a hexadecimal value. This will be a hexa, this will be a hexa, and this will be a hexa. Then I'll be using the lookup table, that is subbyte table. Then I'll replace them with the respective bytes. So after this one, I'm going to perform a subword. After substituting, I'll be getting an output. This output is going to be XOR with another constant value called round constant. Okay. Okay. What is the round constant in the sense? Totally we have we have 10 rounds. Since you are discussing AES 128, for each and every round, totally I'll be having 10 round constants. Like this. For round 1, this is the round constant 1, round constant 2, 3, up to 10. Right. So this round constant will be XOR, and final output which are going to get will be the temporary word. This temporary word T4 is going to be XOR with W0. So whenever you are getting a I value which will be multiple of 4, okay, I value which will be a multiple of 4, okay, this is nothing but the temporary word, okay, that is Ti going to be XOR with Wi minus 4. Right. So whenever, for example, if I go with W4, I'll be getting T4 XOR with W0. W8 means temporary word T8 XOR with W4. Like this, all the multiples of 4 should be XOR with the temporary word and I minus 4th word. Is it clear, guys, the process? Okay, someone, one second. In subword, we basically encrypting the word. Actually, we are doing a substitution cipher. Yes, exactly. We are performing a substitution technique using a subbyte table. Yes, Kashish. Yeah, what you said saying is correct. Yeah. So, anyone have any doubts in this one?
Also, sir, is it always left shift?
Yes,
Not one rotating to one.
always left shift. 1 byte left shift.
Okay.
Irrespective of round, which round you're going to perform, it's only always 1 byte left shift. I hope the process is clear. If it's clear, kindly raise your hand. If you have any doubts, you can ask me. Process is clear means then I will move on to an example. That's what I just said. It's explained here. As I said, why are they are going with subword? As Kashish said, he said that sites look like a you are encrypting the word. Yes, same way. Because of that only, I'm going to give a non-linear relationship because I'm not going to have a one-to-one relationship directly. Right? Simply by using subword transformation, I'm reducing the dependency. As well as this round constant, okay, which are using for each and every round, we're using different round constant. It is the main reason where it guarantees that is each round key will be always different from the previous one. Because one of the major issue with the DS algorithms is nothing but we can't able to use certain set of keys, because if we use those keys we are either getting a pattern of repetition of round keys or we are getting the same key as a round key for all the sustained rounds in DS algorithm. So these issues can be are mitigated using this round constant. Okay, though it has few repetition when you are using weak keys, but it's not going to pertain for all the 10 rounds. We'll see an example here. Right. And this is the same key expansion with respect to polynomial arithmetic. It's mentioned in the book, but for our understanding, that's more than enough. Right. Now we'll see an example here. Right. So here, what they said, instance, here they given the 128-bit cipher key. So here, this is your W0 2475 A to B3. This is your W0. Well, this is your W1, W2 and W3, right? So you can able to see they're using the same given cipher key for a pre-round transformation. without any change. Now we have to generate our W4, W5, W6, W7. We already know W5, W6, W7. It's very easy. Simply you will XOR this two. You'll be getting W5. If you XOR this two, you'll be getting W6. If you XOR this two, you'll be getting W7. Now I have to generate this temporary word. Okay. So T4, right? This is for W4. So this will be my T4. So I need Wi minus 1. That is, I need the word W3. So if we take our W3 word, the word is 13. Yes. 13 AA. Right. 5487. Right. The first step which we are going to perform is nothing but my dot word. Right. Yes, I'm going to rotate it. So I'll be getting AA 54, 87 and 13. This is the first step. Second one is subword. So I have to substitute this one. So I want everyone to note down this value so that I'll show you the subbyte table. So I want you people to tell me the answer after substituting this one. Right. So you have your word as, kindly note it down. Once noted down, raise your hand. Just posted it in the chat box. That is the output. That is the output which we got after our output. Now I'm going to my subbyte table. Once again. Right. Here, using this table, kindly let me know the answer for AA, because using this table you can able to find AA and 87. What will be these values after the subbyte? AA and 87. You can post in the chat box. Then I'll move on to the next slide where you can able to substitute the bytes 54 and 13. So you got AC, okay. Then for 87, for AA you got AC. For 87, right. So now you got AC and 17, right. Now I need an answer for 54 and 13 using this table. 54 and 13. Substitute 54 and 13. 20 and 70. Right. Okay. So now how will the entire block will look like? Can anyone write the entire thing? Entire thing in sense for AA 54, how this one is going to be converted. Yes, so we'll be getting AC. Go back where it just came. Getting AC here. 54 is replaced with 20, then 17 and 70. Third step is nothing but XOR operation with our round constant. Okay, our round constant for round one is simple. Simply 0, 1, if you XOR this one, okay, you just give a try in your home, just simply convert them into binary and XOR, you'll be ending up with this one. AC will be replaced with the AD, then 20, 17 and 70. Because this is simply you'll be getting the same thing. But for AC, we have one bit shift here. Okay. So it's AC would have replaced with AD. Right. And like this you'll be doing for other steps also, for other rounds. Now we'll see some how two cipher keys which have been differing with only one bit is going to produce different round keys which have been totally having a higher bit differences. So you can able to see these two keys having only one bit difference here. Okay, so for pre-round transformation, obviously it will be having the same bit difference. But if you see from round 1 onwards, the bit difference keep on increasing, and you can able to see for 10th round we have 52 bit, for 6th round we have 56 bit difference. So even 1 bit difference, we can able to ensure that the round keys of two parallel AES algorithm, okay, is going to have higher bit differences, right? And here comes the concept of weak keys, which is one of the major drawback in DS algorithm. For example, if you use one of the weak keys, that is all zeros, okay, obviously we'll be using the same thing for pre-round transformation. Up to round 1 and round 2, you can able to see there is a repetition. Okay, unless for round 1, we are using entire thing is repeated for all the words, and round 2, this set is repeated. But after round 2, you can able to see from round 3 onwards, okay, you can able to see at the last round, the key is totally random. Okay. So even you can able to use weak keys in AES algorithm, right? So now if you go with AES 192 and 256, okay, it's the same process with slight variation amount. So in AES 192, okay, the words which have been generated will be grouped in 6 groups. Actually, there is a small correction here. It is up to W5. Okay. So W0 to W5 is totally 6 words. So the 6 words will be grouped. Whereas if you say in AES 128, we'll be grouping 4 words. W0 to W3, then W4 to W7, and goes on. Right. So here you'll be grouping as 6 words. That's all. But here the temporary word will be generated for whenever I is a multiple of 6. Whenever I is not a multiple of 6, I'll be going with this one. Whenever I is taking multiple of 6, then I have to create a temporary word using the same process, okay, to get the output for temporary word here. For AES 256, the grouping will be going for 8 words will be there and it will be grouped. So you'll be having from W0 to W7, which will be 8 words for the first pre-round transformation. Using this, I'll be getting the value, right? Then for whenever it is not a multiple of 8, then I'll go with the conventional way. That is I minus 1 XORed with I minus 8. Whenever I'm getting a multiple of 8, that is your W8, W16, and W24 goes on, I'll be going with a temporary word XOR with WI minus 8. Right. Inside this, okay, this is for multiples of 8. For non-multiples of 8, inside it, we will be having certain words which will be having multiples of 4. For example, if I have W12, okay, for W12, what I will do in the sense, I'll be performing only the subword operation with the WI minus 1. Okay, that is, I'll be performing subword with WI minus 1 as 11, which will go a subword transformation, and it will be XORed WI minus 8, that is W4. Okay, this is just for your understanding. Okay, in examination, you won't ask anything from AES 192 or 256. So if you're clear with the operation with 128, it's more than enough. This is for understanding how this happens. Right? Is it clear, guys? If it is clear, raise your hand. If you have any doubts, so with the discussion we had so far, you can ask me now.
Excuse me, sir.
Yes, Kashish.
For the round constants are same irrespective of whatever questions or like for AES 128, the round constant will remain same always.
No, actually, here if you see the round constants are given only for first 10 rounds. This is the round constant table for AES 128. We have different round constant table for 192 and 250 sets. Okay, since we are not much interested towards discussing 192 and 256, I have not shared those things.
Yeah, so sir, for this 128, this table remains constant, like always.
Yes, always.
So like whenever we are doing AES expansion in 128, we'll always use this table.
Yes.
Okay.
For 192 and 256, we are having different table because their number of rounds is different. Okay, so I have not shared those things. Only for AES 128, that is the table.
Okay, sir.
Okay, what about others, guys? If you have any doubts, you can ask me. If it is clear, raise your hand so that I will proceed further. Now we move on to the final thing, that is the design, the two design approaches. How we had two different approaches provided by DES people, like in DS algorithm, like how we had swappers in 16th round and no swapper in the 16th round, the two different variation. Same way, this is the original design which is provided. You can able to see here we are using a pre-round transformation. We are just having add round key alone. In for round one, we are using our subbyte shift to row, its column add round key, the same flow, and it's going on happening here. But in the inverse process, you can able to see. Okay, first time performing the inverse of my pre-round transformation. Okay, but here you can able to see the entire process totally shuffled here. For example, here you have done subbyte shift row means here you will be doing shift to row then subbyte. Here mix column add round key. Here we are starting with add round key, then we are going for mix column. If you take these two, they are interchanged, right, in our decryption part. This is the original design provided there. That is, you have subbyte shift rows means and sorry. This is the original design. They showed subbyte shift rows are going to be interchanged. Okay, but it causes major confusion in the decryption end. So the alternative approach, what they did in sense, you can go with this way. So if you start with subbyte shift rows, again I can go with inverse subbyte and inverse shift rows. So no confusion. But only condition here, what they said in sense, here you are using add round key. Okay, but here you have to use inverse of that add round key. That is, you have to find the additive inverse of that particular round key, and it should be used in the decryption end, such that your alternate design, how it will look like in the sense, this is the original flow, subbyte shift row mix column add round key, and here the entire process is exactly opposite, mirror image. That is inverse subbyte, inverse shift row, inverse mix column, but here I'll be having an inverse add round key. But in original design, here simple add round key is used here. Okay, but if you're using inverse add round key, that is, if finding the what can I say, the additive inverse of the particular add round key, then if you directly apply there, then I can use the same block with the inverse operations directly here, right? So this is the alternative design, and they also say that you can able to modify the key expansion algorithm also, such that the output coming from this algorithm itself will give me the inverse add round key. No need to find the inverse add round key for each and every round. Separately, you can able to modify the key expansion algorithm such that it can able to give me the output directly as an inverse add round key. So these are two different variants AES algorithm have been proposed. Right, there's a change in the key expansion algorithm. Right, so you can able to see an example here. They have a plain text. Okay, in the respective cipher key. This is AES 128 and the respective cipher text. Here I show the different input state, output, and the round key used. This is a direct cipher key used for pre-round transformation. Simply, if you XOR this add round key with this input state, you'll be getting this output state. You can try in your home. Okay, these are the different operations. I mean, after output of my round one, round two, and goes on. Okay, so here I've given you the key expansion, the expanded version of round 7. And for your purpose, there is an error in one of this flow. I mean, to be specifically speaking, there is an error in one of this 3 process. I want you people to work it out and let me know where the error exists. Okay. So bits column, if you are practice for at least one column, is more than enough. You'll be well versed. But you should practice sub byte and shift rows and add round key for entire state itself. Right. Just kindly practice in your home. Right. Here also you can able to see that if you analyze our AES algorithm with respect to avalanche effect, I hope you remember the avalanche property. That is even 1 bit variation should have a huge bit difference in the ciphertext produced. Here you can able to see we have 2 plain text which are only varying with only 1 bit, right? And they are using the same key, and you can able to see the ciphertext 1 and ciphertext 2 produced, which have been totally entirely different. Right. And here, as I said, they're using the weak key with all zeros and the plain text and the respective ciphertext produced with the weak key is also totally a random one. So with this, we will wrap up today's session, guys. If anyone have any doubt in today's session, you can ask me now.